everybody, my name is Sam Dow, an application engineer from Microsoft. Today I would like to share with you some of the advanced techniques that allows you to extract or obtain the inverse kinematics and inverse dynamic relations based on a MapleSim model. You might have known that MapleSim is an advanced physical modeling and simulation tool that applies model techniques and symbolic computation technologies to produce fast and high fidelity physical models. The symbolic technologies employed by MapleSim allows the user to have a greater insight into the system's behaviors, and that's what we're going to learn today. So we are going to learn how to use Maple symbolic techniques to obtain the kinematics and kinetic relations based on the mechanical systems in MapleSim, and then use the CodeGeneration capability in Maple to generate a C subroutines that can then be embedded with any programs that support C language. Inverse kinematics and inverse dynamics refers to the use of kinematics and kinetic relations to determine the joint parameters or forces that provide a desired position of the end effector. The model that I'm going to be using to demonstrate the techniques is a very simple slider crank mechanism that has been pre-created in MapleSim. The goal here is to use symbolic analysis to extract the necessary information that gives us the desired inverse kinematics and inverse dynamics relations to produce a desired position of the slider, which is our end effector. At first, let's have a look into the system or the model that we have here on the screen. So we have three components or three blocks on the MapleSim screen right now. The component at the top is a parameter block that consists of the parameters that describes the physical parameters of the slider crank mechanism. And the second component is actually a subsystem. It's for the plant model for the slider crank mechanisms that we're going to be talking about, and we're going to be using these subsystems to generate the equations and then obtain the inverse kinematics and inverse dynamic relations. And the third block is a time lookup table that contains the profile data for testing the inverse kinematics and inverse dynamic relations that we will be obtained afterwards. We can double click on the subsystem at the middle, which is for our plant model, in order to see the internal structure of our slider crank mechanism. So let's do that. So we can see now is the internal structure for our slider crank mechanism. We can see there are two cranks linkages that are connected to each other and also connected to the ground through the two revolute joints R1 and R2, and the second crank is connected to a mast through a third revolute joint R3, and the mast is connected to the ground through a prismatic joint P1. So the mast here is our slider. And also in this model I have included the three sensors at the two revolute joints and the prismatic joints that allows me to plot the angular velocity, angular acceleration, the displacement, velocity and acceleration of the three joints of interest. And I'm applying a sinusoidal profile to the drive crank R1 in order to generate the plots that allows me to use them as the sample profiles for testing the inverse kinematics and inverse dynamic equations that we are going to obtain afterwards. So we can run this simulation very easily by simply clicking on the triangle button at the top here. So let's try to do that. So once I click on this button, you can see that something's going on at the console window at the bottom here. So MapleSim generates the equation, it runs the simulation, and then it gives you the plots. So when the plot window appears, you can see that we have the plots for the drive torque, the plot for the theta1 angle. So theta1 is the angle of the drive crank. And we can also see the plot for theta1 underscore d and theta1 underscore double d, which are the angular velocity and angular acceleration for the drive crank. We can also see the plots for theta3 underscore d and theta3 underscore double d for the revolute joints connected the second crank and the slider mass. And we also see the plots for S underscore D, and S underscore double D, which are the displacement, velocity, and acceleration of the slider. So these plots are corresponding to the probes that I have placed in the MapleSim model that you see here. So once you obtain the plots here, you can save the plots data to an Excel file that can then be used as the profile for testing the relations or the equations that we are going to get afterwards. So let's if you click on the button here, you can save this plot data to an Excel file. So you can select the format for the file, which can be a CSV file, or it can be an Excel format. So you can override the files that I already have on the hard drive right now, which is the profile data file, and you can save it. Okay, and after you have saved the plot data, you can attach that to the MapleSim model and use that as in the lookup table for testing the inverse kinematics and inverse dynamic relations. So let's double click on the test data that I have attached to the MapleSim model here. So once I click on datasets folders, you can see that there's an Excel spreadsheet called profile data.xls. If you double click on that, you're going to be able to see the data in the Excel file. So the first column is the time, the second column is the drive torque for the drive crank, and you can also see theta 1 underscore D, theta 1 underscore W, which are the angular velocity, angular acceleration for the drive crank. You also see the data for S underscore D, and S underscore D, which are the displacement, velocity, and acceleration of the slider. So we're going to use this data by pointing the lookup table that I have on the screen here and pointing that to the data file, to the Excel files that you have. And in order to extract the right data, you can specify the column number. So I'm extracting the column number 3, 4, 5, 6, 7, and 8, which are corresponding to the angular velocity, angular acceleration of the drive crank, the displacement, velocity, and acceleration of the slider. In order to extract the inverse kinematics and inverse dynamic equations, we're going to use a Maple worksheet that I have prepared to do the things. So let's go ahead and do that. So I am going to click on the project tab and go to the documents folder, and I open up the Maple worksheet called analysis.mw. So we are in a Maple environment now. So this is a special Maple worksheet that consists of the Maple commands that allows me to extract the equation from the MapleSim model and then extract the inverse kinematics and inverse dynamic relations from those equations. So at first I need to select the subsystems that I want to get the inverse kinematics and inverse dynamic relations for, which is our plant model or the plant subsystem. So I'm going to select that from the drop down menu here. So once I select that, you can see that the internal structure for the subsystem has been displayed on the screen. The Maple worksheet has been organized in 4 different sections that are called initial setups, forward kinematics, inverse kinematics, and inverse dynamics. So this section consists of the Maple commands that I will go through in a moment. So let's open up the first section, initial setups. So, the first command in this section consists of the Maple commands that allows me to load up the packages, the helpful Maple packages for plots, CodeGeneration, which allows me to generate C code from the equations, and the MapleSim tools package. Okay, so I'm going to execute this command line. The second command allows me to link to a MapleSim model and then assign that MapleSim model to a variable that I named M model. I'm going to execute this command as well. The third command allows me to extract the multibody dynamic part of the model. Okay, so I'm going to use option simplify equal true, which will allow me to simplify the output equation. So once I execute this command, Maple will formulate the symbolic equations and then generate the symbolic equations based on the information it grabbed from the MapleSim model. So you can see that these are some of the variables. P underscore S is the displacement of the slider. R1 underscore theta of T is the angle of the first revolute joint, the revolute joint R1. And R3 underscore theta is the rotational angle for the revolute joint R3, which is the revolute joint between the second crank and the slider. And we also see the vector for the angular velocities as well. For the velocity and angular velocities as well, and also the acceleration vector, as well as the reaction forces for Fx and Fy. I'm going to also define a list of the 4 parameters that will allow me to conveniently use this for testing the equation or the code. Okay, so I'm going to execute this. So the 4 parameters have been defined in a list. After that, I want to replace the long name variables by the short variable. So for example, I want to replace R1 underscore theta by simply theta 1, and R3 underscore theta by simply theta 3, and P1 underscore S, which is the displacement of this slider, by simply S. So I'm gonna store this in a vector, and after that I can substitute this vector or substitute this list into the equation in order to replace a long variable by the short variables. Okay, so the next step I want to call the get positions command in order to extract the kinematic relations based on the multibody dynamic equations. So I'm going to execute this command, and as you can see that I also call the subs command to replace the long name variables by the short name variables. So the constraint equations, so after I call this command, you can see that I have obtained 2 constraint equations, and these constraint equations are the function of theta 1, theta 3, and S, and we're going to be using these constraint equations in order to extract the forward kinematics, inverse kinematics, and inverse dynamic relations. So at the first step, we are going to use these position constraint equations to obtain the forward kinematics equations or relations. So let's expand this section and then learn how to do that. So for the forward kinematic relations, we are going to use this constraint equation to obtain the expressions for the slider position as a function of the drive crank angle. So the goal here is to obtain the position of the slider in order to get the desired position of the crank angle. So the first command, the first command line here, I'm using the solve command, and based on the position constraint equation, I'm gonna be solving for the 2 variables, S of t, which is our slider position, and theta 3. So theta 3 is the angle of the revolute joints between the second crank and the slider. So theta 3 is solved as a byproduct of the process. Because we have 2 constraint equations, we need to solve for the 2 variables. Okay, so let's execute this command and do that. So here we can see that we have obtained the expression or the solution for S of t, which is given as L1 times cosine of theta 1 plus root of L1 square sine theta 1 square, and the other terms. So root of is the placeholder for the solution, and we need to evaluate the solution for S of t in order to obtain all the solutions for S of t. And we can also see the solution for theta 3 as well, but we are not interested in the solution for theta 3, and we are going to be using the solution for S of t only. So next we are calling the all values command and evaluate the solution for S, and that allows me to get the 2 solution for S. So for each crank position, we can have 2 positions for S, and this show up as the 2 solutions within the square brackets here. So now we have 2 solutions for S. How do we know which solution are we going to be choosing? So in order to select the right solution for S, we are going to plot both of these solutions, and we're going to see what solution we are interested in. So there are 2 solutions. One gives us the positive S, and the other one gives us the negative S. So we're interested in the positive S, which place the slider on the right hand side. Okay, so we're going to select the first solution. So the red curve is corresponding to the first solution. So we're going to select the first element of O underscore S underscore source, which gives us this expression. So this is the solution for S, and this is our forward kinematics relations based on the constraint equations. So for the next step, we can generate a C code for the forward kinematic relations, and then we can use the external C code template in MapleSim to test the C code and incorporate the C code into MapleSim model as a custom component and test that and run the test in MapleSim. So at first, we're going to grab all the equation for S of t, and we're going to put that in a separate list that I call equations, EQS. So the next step, I want to define the list of I want to extract the list of parameters that are used in these equations. So I call the index command, and I can then extract all the parameters that appears in the equation for S of t. And after that, I define a list of default parameters. Okay, so based on the default parameters that I defined at the beginning of my worksheet. So there are 2. So the default parameter for L1 and L2 are shown in here. So L1 takes the value of 1, and L2 takes on the value of 2. And after that, I will be calling the a special procedure that I wrote, which is called external C CodeGen. So this function allows me to save and generate a C code based on the equation, and then save that as a C procedure or C subroutine that can be easily embedded with any programs. So this command, this procedure takes in several parameters. First, you need to define the path for the file, for the C file. So I'm going to call it fwdkin.c, and I need to define the name for the procedure, and then you can pass in the equations that I want to get the C code for, as well as the list of default parameters. And I want to save I want to store the parameters, the input parameters and the output in separate vectors that I call param, inp, and out, which stands for parameters, input, and output. So I'm going to execute this command. And after that, you can also attach the C file to the MapleSim model. And I'm going to attach that to my MapleSim model and put that under the folder other. Okay, so let's execute this command as well. So if you go back to the MapleSim now, and if you click on the folder others under project, you will see that the C file has been generated and attached to the MapleSim model. So next step, I will be using exactly the same procedure in order to extract the inverse kinematics and inverse dynamic relations from the equation as well. So based on the same set of constraint equation, I'm now solving for theta 1, which is the angle of the drive crank, and theta 3. So this allows me to obtain the expressions of theta 1 and theta 3 as a function of the crank position, and that will give me the inverse kinematic relationship. As well, you can see here theta1 is given as an arctan function, and it has a placeholder for root of. So we need to evaluate this expression by calling the all values command, which coming next. So the all values command allows me to evaluate and obtain all the solutions for theta1. So theta1 has two solutions, which are given by the arctan functions. Okay, so in order to know which solution we are going to be selecting, we need to call the plot command in order to show all the solutions on the screen, on the plots. Okay, so we're going to be plotting all of these two solutions on the plots right now. So you can see that for each position of the crank, we can have two solutions for the drive crank angle. So for each position of the slider, the crank can be up, can be above the ground, or can be under the ground, which is corresponding to the elbow up and elbow down configuration. So based on the plots here, we are going to be selecting the elbow up configuration, which gives me the positive theta1 angle. Okay, so that comes next. So I'm going to be extracting the first solution from the list all theta solutions. Okay, so that gives me this. So this is my solution for theta1. So the next step is very similar to the section on forward kinematics. I'm packaging all the equations for theta1 into a list that is called EQS. I'm extracting the list of parameters that are used within this equation as well. That gives me a list of two parameters, L1 and L2, which are the lengths of the two cranks. And I will also assign the default parameter to these two parameters for testing later as well. And after that, I also call exactly the same function to generate a C code based on this equation. So I'm calling the external C code gen equation, and I define the name for the inverse kinematic C code and functions, and I pass in this procedure a list of equations, default parameters, and also the name of the input parameter and output. So I'm going to execute this as well. So after that, I can also save the C code to the MapleSim model by calling the set attachment command. So once you do that, if you go back to the MapleSim model now, and under the other folder, you can also see that the C file for inverse kinematic has been generated and attached to the MapleSim model. Finally, you would like to use the same procedure in order to extract the inverse dynamic equations as well. So that's what we're doing next. So at first, I would like to list all the necessary equations for that can be used in the inverse dynamic equation. So in the inverse dynamic equation, we would like to determine the torque that can be generated by the drive crank in order to give me the desired position of the slider. So this information can be helpful for the open loop or the forward control for the slider position. So at first, I'm going to list the solution for theta1, which we have obtained in the inverse kinematic sections. The torque equation also includes the equation for the angular velocity and angular acceleration for the drive crank. So we are going to, in order to get the angular velocity equation, all we need to do is to differentiate the solution for theta1 with respect to time. Okay, so you can see that the equation for the angular velocity is pretty big, so you can hide the result by typing colon at the end of the command line, and you can differentiate the equation for theta1 twice to get the angular acceleration for the drive crank angle as well. Okay, so if we execute this command and print out the result, you can see that the result is it prints out a pretty big equation. and that can be hidden by simply typing the colon at the end of the command line as well. So let's do that. The equation for the drive crank torque also includes a variable for the third revolute joints, R3. So as you can remember, the solution for R3 has been obtained in the inverse kinematic section as well. So as a byproduct of the solution. We can solve for the solution of theta 3 in exactly the same ways as we did for theta 1. So I'm going to be calling the all values command to evaluate both solutions for theta 3, and we can also plot theta 3, put that on the graph in order to select the right configuration. So we're selecting the positive solution for theta 3 as well, and that's what I'm doing here. And again, differentiate theta 3 the one time to get the angular velocity equations, and differentiate that a second time in order to get the equation for the angular acceleration for the third revolute joints. In the next step, I would like to extract the equation for the drive torque at the drive crank, based on the dynamic equation of the system. So if you still remember, if I scroll up here, you can see that the dynamic equation of the system consists of three equations. And in order to solve for these three equations, or the three ODEs, Maple requires that you define a list of three variables that you want to solve for. So I'm going to go ahead and define a set of three variables that I want to solve for. So these are Fx, Fy, which are the reaction forces on the slider, and the third variable is R1 underscore M. It is our main variables of interest. It is the variable representing the torque for the drive crank. So I'm going to execute this. Now I can call the command get dyne equations in order to extract the dynamic equations, or the ODE, for the slider crank mechanism. And I will store this equation in a variable that I named DIN EQS, or dynamic equations. So now I have in the results that is printed out, you can see a set of three ODEs that have been extracted from the system. So now I have the dynamic equation of the systems that are the functions of the variables of interest. I can go ahead and solve this equation for the solutions for Fx, Fy, and R1 underscore M. So I just go ahead and call the solve command, solve for the dynamic equations, and it will solve for the solution for the variables of interest. So I just execute this, and in the result you can see I get the solution for Fx, I got a solution for Fy, and I got the solution for R1 underscore M, which is again the torque for the drive crank. Since I only need to use the equation for R1 underscore M, I will extract that from the equation above, from the list of solutions above. Okay, so I will call the serve command, and I will extract the equation for R1 underscore M, so which is given by this expression. I will assign this to a new variable that I call crank torque equations. You can also call the index command to extract the list of parameters, variables, and functions used within a certain expression as well. And this is a list of parameter, variables, and functions that are used in the crank torque equations. I also want to define a vector that allows me to replace the function, the differentiation function for theta 1, theta 3 s by the short variable that which will be convenient for CodeGeneration later. So I'm going to replace the derivative of theta 1 with respect to t by theta 1 underscore d, and the second derivatives of theta 1 with respect to t by theta 1 underscore double d, and I do the same thing for theta 3 S. The equation above also consists of two extra variables, which are P1 underscore F and R1 underscore M. These are the reaction force and torques for the joints where I attach the sensors to. So once you attach a sensor or a probe to a MapleSim component of joints, then Maple would automatically generate the equation that includes the torque and force equation corresponding to where you attach those sensors or probes. I'm going to execute this command to define this substitution list. Finally, I want to grab all the equations that allows me to calculate the crank torque. So these are the equation for theta 1, which has been obtained in the inverse kinematic sections. Okay, so theta 1 is defined through theta 1 underscore sol, and I also have the solution for theta 1 underscore d, which is the angular velocity for the first revolute joints. I also have the solution for theta 1 underscore double d, which is angular accelerations. For the drive crank revolute joints. I also have the solution for theta 3 underscore d, theta 3 underscore double d, and finally I have the equation for the crank torque. So I just go ahead and execute this in order to store all of the equations into a variable that I call inf_dyne equations. You can also call the index command in order to figure out how many variables are used within these equations. And at the same time, you can also extract the list of parameters. So as you can see, there are 5 parameters that are used in these equations. These are L1, L2, M1, M2, and MS. So these are the lengths of the linkages and the masses of the linkages and the slider. You can also assign the default parameters to these parameters as well. And finally, I call the external CodeGen command, and then save and then generate the C code from these equations. And then after that, I save this C code file to the MapleSim model. So if you go back to the MapleSim model now, you would be able to see that the C code file for the inverse dynamic procedure now has been saved and attached to the MapleSim model with the name inf_dyne.c. You can view the C code in this file by simply double clicking on them. So let's say double click on this file, and on my computer loads up Microsoft Visual Studio and open up the C code files that allows you to see the C code. Okay, so this is the structure of the C code. You can see this is in the common out section. You see that we have a list of parameters with the default values, the list of variables, and the list of outputs. And these are the name that we have been using for the C component. Okay, and this is the main body of the C function. So the C code, the optimized C code has been generated by Maple CodeGeneration package, and the expressions are evaluated in a in a specific sequence that allows it to speed up the computation. In order to view the actual C code, you can double click on one of these files. So let's say I double click on the inf_dyne file. And my machine opens up the Microsoft Visual Studio that allows you to view the C code, the actual C code. So this is internal structure of the C code. So at the top are the packages or the library that is loaded for some of the special function used in this C code. And follows that is the compiler directives. And in the common out section here, you can see that these are the list of parameters, inputs, and output variables with the namings that you have chosen to define for the C function. And here is the main body of the C functions that has been generated by the Maple CodeGeneration package. So the expressions that has been converted to C code has been evaluated in a particular sequence that, according to Maple, is the fastest way to evaluate those expressions. So now we have the C code for the forward kinematic, inverse dynamics, and inverse kinematics. You can use the MapleSim external C code template to test these C code functions within MapleSim environment. And that's what I'm going to be doing next. So now I'm going to click on the paperclip icon that would give me access to the external C library block template. So let's open it up. Okay, so this is a special template that allows you to read the external C code and then generate a MapleSim custom component from it. So at first I want to test the C code for let's say inverse kinematics. So I want to give it a name in MapleSim, inverse kinematics. And I want to point this worksheet to the file, to the C code file, which is inverse kinematics. And the next step is to define the input and outputs for the code component. So first, I want to define the name. I want to have to specify the name for the function. So the C code file can contain several different functions, and you need to tell this template what function you want to call. So this is a function you want to call inv_kin, which is a function that allows me to calculate the inverse kinematics. And the next step, I want to define the input and output ports for my component, for my custom component. So the first port is the input port for parameters. So let's go back to the C code here and open up the C code file for inverse kinematics. So you can see that in the common out section, we have two parameters, one input and one output, and that we're going to be using this information to define the input and output for the component as well. So I have two parameters, and I want to define that as an array with two elements, and I click on add parameters. I do the same thing for the input. The name of the input parameter and output ports have to be exactly the same as they are defined in the C code file. So I want to define another variable for the input as well, and I click on add parameter. The output also has one element, and I check the box passed by reference to indicate that this is an output, and I click on add parameter button again. So return, my C code function doesn't return anything. It's a void function, so I uncheck this box, and then I click on the button generate external code component. That would allow my template to generate the C code, the custom component block based on the C code. So it has been generated, as you can see on the screen here, and you can drag and put that onto the canvas. You can do the same thing for the inverse dynamics. So in order to generate the component based on the C code for inverse dynamics, I need to go back to the C code file again to see how many parameters, inputs and outputs are. So I have 5 parameters, 3 inputs and 7 outputs. And the torque, the torque variable is the last output. It is the main variable of interest. Okay, so I go back to the same template, and I want to change the name for the block. I want to call it inverse dyne or inverse dynamics, and it points out to a different file for inverse dynamics. I will select the inverse dynamic C code file. I will also give it a different name So this is a name for the inverse dynamic procedure. Now I need to clear all the table because the size of input, output, and parameter vectors are now different. So I want to define param. Okay, so I have 5 parameters, 3 inputs, and 7 outputs. Now I'm ready to generate the custom component for the inverse dynamics. So it has been generated and placed under definition section of the model. So I just put that onto the canvas now. Now I have the MapleSim custom component based on for the inverse kinematics and inverse dynamics based on the C code generated from my Maple worksheet. I can use this for testing and then compare the result with my plant model. So as you already know, I have the test profiles which was generated from the previous simulation of the main plant model, and I will be using this for testing the C code custom component. So this is the lookup table that will output the result for theta. So now I have the two MapleSim custom component for inverse kinematics, inverse dynamic. I can go ahead and do a few tests and then compare the result with my simulation result from my main plant model. And in order to do the test, I would need to use a profile that was generated based on the previous run based on the plant model. So the lookup table here consists of the signals or the data for the profile data for the rotation, angular velocity, angular acceleration for the drive crank, and displacement, velocity, and acceleration for the slider. I'm going to be using this for testing the two new custom components that I generated. So since this lookup table outputs 6 signals, I will need to split it up into 2 vectors with 3 signals each. In order to do that, I'm gonna need a demultiplexer component in MapleSim. So I go to signal blocks and I pull out a real demultiplexer component. I want to define 2 output vectors with 3 elements each, and I can connect that to this lookup table. So the port at the top of this demultiplexer component gives me the angular velocity and angular acceleration for the drive crank, and the port at the bottom gives me the displacement, velocity, and acceleration for the slider. The 2 custom component block here also requires the 2 input vectors for the parameters. So I need 2 parameters for the inverse kinematic components and 5 parameters for the inverse dynamic component. So I with a constant vector, and for inverse kinematics I need 2 parameters, L1 and L2, and it takes just a scalar signal for the input, which is the displacement of the slider. So I need a signal extract signal block with 3 inputs and 1 output, and I want to extract the first signal from a second input port, from a second output port of the demultiplexer component. I will then connect that to the inverse kinematic component. I also need to define the input vector for the inverse dynamic. So the inverse dynamic component requires 5 parameters: L1, L2, M1, M2, and MS. And then I can connect that to this port. I can also connect the output port, the second output port of the demultiplexer component directly to the input port of the inverse dynamics, because the 2 vectors have the same size. So now I can attach the props to the inverse kinematics components. I call it in out, and to define the props for the inverse dynamic component as well. I'm interested in getting the last signal, which is my drive crank torque. So I check the box for that. So now I'm ready to run the simulation. So in a few seconds, MapleSim would give you the simulation results in a new window. Okay, so now the simulation has been completed. You can see the result now. So in the simulation results here, you see the first plot, which is a drive torque generated from the main plant model, and the second plot is a drive crank torque generated from the inverse dynamic block. So you can see that they look exactly the same. In order to compare them with each other, you can simply create a new plot window. So I'm going to do that. I'm going to click on the signal for the drive torque, and I will drag the output, the signal from inverse dynamic output, and put that on top of the same plot. So you can see that the two plots are exactly overlapping with each other. I can do the same thing for the angle of the drive crank. Okay, and I can get the same signal from the inverse kinematic as well. So you can see that the two signals are exactly overlapping with each other, and you can also rearrange the plot so that they can sit side by side with each other as well. And you can follow the same procedure and then generate a custom component for the forward kinematic and do the same and do the same plotting as well. And this concludes my presentation today. So as you can see that MapleSim is a very powerful simulation, physical modeling and simulation tool. And with the Maple symbolic engine under the hood, you can do a lot more than just running the simulation in MapleSim. You can use Maple to extract the equation and then do analysis on the equation to get the inverse kinematics, forward kinematics, and inverse dynamic relation from based on the equations extracted from the MapleSim model. And you can also generate a C code and then bring those and then bring the generated C code into MapleSim model to run the simulation as well. Thank you for your attention.